on 2 of the homework questions. First one, let me reshare my screen just in case. I'm trying to make sure I have the problem number right. There we go. 4.1, number 32. This is the one where it's like the ax squared plus bx plus c, and it's asking for critical points. If you haven't figured this one out already, your answer should be some kind of fraction. So, you know, it's not going to be d over e, but it's going to be some fraction. So when you put it into Wiley, you need to put the denominator in parentheses, or else it's not going to accept it. So a lot of you have been getting the right answer. It's just that the denominator didn't have parentheses around it, so Wiley doesn't accept it. That's specifically because the denominator has 2 things in it, and if it's not in parentheses, it reads the last term as being multiplied instead of part of the denominator. So anyway, you'll need parentheses for that one. And then the other one that's kind of just wording. Oh man, which one is it? Is it this one? Yeah, okay. So then 4.3, number 40, you'll have some kind of equation. It changes for everybody, but you'll have some kind of equation that looks, you know, something like this. And you're asked to maximize or minimize it. And it specifically says global max min values. So it's a very nuanced thing. When it asks for the values, it wants the y values. So you want to put in the y values as your answers instead of the x values. So a lot of people, again, have been finding the correct x values and trying to plug them in and then not realizing that it wants the y values, which is slightly understandable. I realize if you missed that word or don't realize that that word is trying to tell you y values. So those are 2 points on the homework that have been pretty common. So yeah. Haley, I'll go ahead and look at that after class and see what's going on, and I'll email you about it. Actually, let me just, if I can do this super quick. Let's see how fast Wiley allows me to do this. Probably not fast enough. But anyway, let me start erasing this while that tries to pull up. Doop, doop. Doop, 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 doop. So while I'm trying to pull that up really quick, Haley. So we got to talk about 5.2 today. So remember in 5.1, we talked about, so that all of those notes I just made will be in the recording if you need to look at them later if you missed it. Brain. So we got to talk about 5.2. Now 5.2 is a somewhat weird section. Haley, why does it say I already corrected it for you? I'm so confused. Haley, on my side, it registers that I gave you full credit for that, like, already. I don't know when that happened. Okay, okay. Magic. So I thought it showed up on your side too, but yeah, on my side, that one is fine for you, Haley. All right, 5.2. 5.2 is a little bit of a weird section because we don't gain a lot of new material from it, really. The main point of 5.2 is to really build up a definition that we need to talk about. So the first thing we need to talk about is something called sigma notation, which is a little bit of a side note. We don't really do a lot with the sigma notation. We just need to understand what it means to be able to understand the definition that I'm going to write. So you won't need to really do much with the sigma notation. You'll just want to realize what it means when you see it. So sigma notation enables us to write a sum that has many terms in a compact form. So say I wanted to, well, no, let me do the generic one first. So I'm going to write a generic one to begin, and then we'll do some with some actual numbers in a second. So say I have some generic sigma notation. This is what it would look like. So that symbol on the right is just the Greek letter sigma, if you didn't know that already. And in math, it usually is used to stand for sum. So essentially what this is saying is so the other thing about sigma notation is the sums that they can write, the things that they can, the sums that sigma notation can be used for specifically have to have a pattern in the terms. So you can't just take absolutely any sum. There has to be some sort of pattern. Maybe I should be careful with the word pattern. But there needs to be kind of a common relationship between all of the terms. So here, essentially what we'd be saying is we'd be saying that we're plugging in values to some x sub k. And the values we're plugging in, we're going to start with 1. And we're going to keep going up the integers until we get to n, whatever n is. So in this case, we'd essentially say the first term is x sub 1, the second term is x sub 2, and we would keep adding terms until we got all the way up to x sub n. So I know that's very generic, and again, we'll do one with some more numbers in a second. But that's essentially what sigma notation is doing. It's taking this, really long sum that has a bunch of terms and being able to write it really succinctly. So now the point of using sigma notation for this definition is, remember in 5.1 we were doing Riemann sums, which was our, areas of rectangles that we were summing up. And if you remember back to the example we ended on last time, there was like the one that we did full out, the last one we did had 10 terms to it. And then specifically, the question then asked for the 20 term one, but we just talked about that one. We didn't actually find it. So sigma notation would be a really nice way to write that, 20 term sum in just, this small kind of compact way. So anyway, so the Greek letter stands for sum, and then we have something called the index of summation. Index of summation. That's going to be that k. So that's going to tell us where the sum begins and where it ends. So in this case, it told us that we start at 1 and we end at n. Now, any letters can be used there. That could be, a equals 1, z equals 1, whatever. But usually I, j, or k are used. So 2 more examples that are have a bit more numbers to them. So we had k equals 1 to 5, and then we were just doing k. So that means the things that we're going to sum up are going to look like just some k value. And so our index of summation is telling us to start at 1. So we start at 1, and then we essentially keep plugging in new numbers to this k value until we get up to 5. And we just go with integers. So 1 plus 2 plus 3 plus 4 plus 5. So now writing this sum out isn't terrible, but say you wanted to write the sum of the first 100 integers, and you didn't want to write 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 plus 8 plus 9 plus 10 all the way up through 100, you could write it in sigma notation from k equals 1 to 100. One of my screens is lagging a lot. All I did was box the sum, but it's not showing up. There it is. Or say we wanted to do something like k equals 1 to 4. Let's not go too far. Let's not go too crazy. Of some 2k. So essentially this is telling us that the things we're plugging in are going into k. So we're going to have 2 times 1 plus 2 times 2 plus 2 times 3 plus 2 times 4. So we start at 1 and we keep going up the integers until we hit 4. My screen's lagging again. And of course you could simplify them along the way. You could actually find them in each step. You could say 2 plus 4 plus 6 plus 8. But I wanted to write them out in that kind of very generic way to show you that the pattern holds for each term. And again, let me stress that we're not doing a ton with the sigma notation stuff. I'm just trying to get you to understand it enough to be able to understand the definition we're going to have to build up to in a second. But say we wanted to look at this, express the sum 1 plus 3 plus 5 plus 7 plus 9 in sigma notation. Now, this is going to take a little bit of trust and believe me, in case you haven't seen this definition before. If you didn't know, the definition of an odd number let's say a number n is odd if you can write it as some 2k minus 1 for some integer k. So it's a little bit of trust and believe me if you've never seen this definition before. And I mean, it's a definition, so you just have to assume it's true. So this is saying that any odd number can be written as some 2k minus 1, where k is whatever it needs to be. So any integer you give me, I should say any integer it needs to be. So any integer you give me, if I plug it into 2k minus 1, I'm going to get an odd number. If you give me 0, I'm going to get -1, which is odd. If you give me 5, I'm going to get 2 times 5 is 10 minus 1 is 9, which is odd. Absolutely any integer you plug into 2k minus 1 is going to be odd. Why do I say that? I say that because 1, 3, 5, 7, and 9 are all odd. So essentially, this is why I was careful with the word pattern. The relationship, the pattern, if you will, of all of those terms is that they're odd. So all of them can be written as some 2k minus 1, so that's what I'm going to use for my sigma notation. Now I need to figure out where to start and where to end. Well, my starting term is 1, so I want to choose the correct k value such that when I plug it in 2k minus 1, I get 1. Well, if I let k be 1, then I get 1. 2 times 1 is 2 minus 1 is 1. So we want to start at 1. And I want to go all the way up to 9. So 9, what k value do I have to use such that when I plug it into 2k minus 1, I get 9? Well, if I want 2k minus 1, I'd essentially need a 10 for the 2k. So that means I would have to plug in a 5. So I want to stop at 5. So this would be my answer to the question, but just to go a step further to prove that that's exactly what I wanted it to be. If we were to write this back out, we would have 2 times 1 minus 1 times 2 minus 1 plus 2 times 3 minus 1 plus 2 times 4 minus 1 plus 2 times 5 minus 1, which is 1, 3, 5, 7, and 9. And my screen is super laggy. So all you need to know about sigma notation is that we can write these sums in this compact way. Okay, because now I have to build up to this definition that we have. This definition is probably the most notationally scary definition we have. So the first part I'm going to write down doesn't look that bad, but then when I write out the formal definition, it's going to be pretty notation heavy. It's just a definition. Don't freak out. It just is a gross looking definition. But anyway, you'll see what I mean in a second. So suppose, are there questions before I go on to the definitions? I'll wait like 5 seconds. Do I have my sound up? Do. Okay. So suppose f is continuous for some interval, so essentially almost every function we'll ever work with. The definite integral of f from a to b is written in the following way, and then I'm going to actually define it. So I haven't defined it yet, but here's the notation for it, and I want to talk about the notation really quick before we go on to the formal definition. So that's the notation we're going to use for this thing called the integral. The a and the b, those are going to be numbers, and they're called our bounds. And that f of x is going to be called the integrand. So if you ever hear me use those words, that's what I'm talking about once my screen catches up to me. As always, I don't know if yours is as lagging as mine, but I'll wait for that one to catch up. And if yours is extra laggy, just let me know. Now, that dx in the back, it does technically have a meaning. It's not that it's useless. But in terms of our class, it doesn't really mean a lot to us. In further calculuses, it means it's very important. But in terms of what we do for our class, it doesn't really do much, but tell us what variable we're working with. So don't freak out with that dx notation. It doesn't really do anything for our purposes. But it does need to be there. Let me be clear about that. So I haven't actually defined what this thing is. So what is the definite integral? It is the limit of the left-hand or right-hand sums with n subdivisions of that interval as n gets arbitrarily large. In other words, if x sub 0, x sub 1, and x sub n are the endpoints of the subdivisions, we have our nasty looking definitions. Before I do that, before I write down the nasty looking definitions, let me draw a picture over here. Just a, basic function. So remember with our Riemann sums, we're essentially breaking this up, into different pieces, right? Into a bunch of different rectangles. So what they're saying is essentially let the x sub 0, x sub 1, and so on be the names of the places where you're breaking it up. And essentially what we're going to do is we're going to let n be arbitrarily large, which means that eventually we're going to have an obnoxious amount of rectangles. I think I kind of said this the other day. I can't remember if it was your class or a different class. But remember, we're trying to estimate area here. The more rectangles we use, the better the estimation. So if we could use infinitely many rectangles, we would find the actual area. And that's exactly what this definition is saying, it's saying we want to take, so we're saying that the integral from a to b of f of x dx, and we have two different things that are equal to it as well. This is going to be the limit as n approaches infinity, which essentially means let there be infinitely many rectangles, infinitely many subdivisions. There we go. So if n goes to infinity, and we're going to take the sum from k equals 1 to n of f of x sub k times delta x sub k. Now, let me write out the other one, then I'll talk about what the heck that sigma notation is actually trying to say there in a second. This is what I meant by this is the scariest looking definition we probably have in this class. So what is that sigma notation actually trying to say? And this is why we had to talk about it a little bit, just so that you knew what the notation was. These are your Riemann sums. Let's see, the top one is the right-hand side. Because if you think about it, if we're going from 1 to n, that's essentially telling you that you're taking these values to be the heights. So that f of x whatever is the height, and the delta x is the width. So that is essentially a height times a width. So that sigma notation is essentially telling us a sum of areas of rectangles. And then the bottom one would be the left-hand side, because essentially we're starting at the 0 endpoint and going up to everything but the last one. So those two kind of freaky looking sigma notations are just a very generic way of writing a Riemann sum. So all these definitions are saying is that we're defining the integral to be a Riemann sum for infinitely many rectangles, which we can't, add up an area of infinitely many rectangles by hand. But if there's another way we can calculate these integrals, then it'll be what we want. So we will be learning how to do the integrals by hand, not with rectangles, but we will be learning how to do the integrals by hand. In just a second, we'll see how to do it on our calculator. But again, in a few days, we will see how to do them by hand as well. And sometimes you can't use your calculator. There's two examples at the end of this section that you can't use your calculator for. So don't rely too much on your calculator. But again, just a definition. Don't freak out too much about the scary notation. It's just saying that we're defining this integral to be essentially the area underneath of the function. So if we consider the last example we did in 5.1, so that was the one, let me actually pull it back up really quick. go back to it for just a second to remind us what that looked like. So the last example in 5.1 that we did on Friday was this one with, oh, sorry, this is from my other class and they never actually finished. I need to go to yours then so that it can actually be filled out. So it was that one where we had to find the table because we had to find the values. And then we had to find the left-hand sum for a couple situations. And now this is taking too long. Whoopsies. Come on, scroll. All right, I didn't put it, oh, okay. I don't know where it went. Apparently I didn't post the notes and no one called me out on it. So they're not there. They'll be up there later. Anyway, so that was a bust. Anyway, sorry about that. So it was a problem where we had to find a bunch of Riemann sums. That's not there anymore. But say we wanted to write that Riemann sum as an integral now. So we want to take essentially the area underneath of this function between 0 and 20, and we were given this function of 3 plus 0.1 t squared. So if I wanted to write that thing that we were calculating the other day in integral notation, what we would do is we would have an integral from 0 to 20, because those are our bounds, because we're over the 20-hour period. And we would just have that function as our integrand. Now it would be a dt in the back because whatever variable is on the d whatever has to match the variable that's in the equation. But again, in terms of our class, that dt doesn't really do a lot for us. It just essentially tells us the variable that we're working with. So that's how we could write those. Essentially, we were estimating this thing with those Riemann sums the other day. Now, say we want to do this with a calculator. Now, if you have a different calculator than a TI-83, 84, or Inspire, you can email me, but I'm probably going to have to Google it anyway, so you might just want to Google it. But if you have a TI-83, an 84, or an Inspire, I will show you how to do it right now. So say we wanted to calculate that definite integral in our calculator. So the first thing is I'll do it for a TI-83 or 84, and then I'll show it for the Inspire. And again, if you don't have one of those, then I'm sorry. You're going to be tuning out for a couple minutes because I don't have anything for you. But say we want to use this function that we just wrote down, the integral that we just wrote down on the previous page, the integral from 0 to 20 of 3 plus 0.1 t squared dt. So I'm going to jump over here. If you have a TI-83 or 84, now if it's an older 84 or it's an 83, you'll have to hold on a second because your ending notation is going to look different, but the starting point's going to be the same. So what you're going to do is I'll give you all 2 seconds to grab a calculator if you don't have it in front of your face already. So what you're going to do is you're going to hit the math button, which is underneath of the alpha. Why is it not? There we go. Math button. Now you can either scroll down to number 9 or you can just literally hit the number 9 on the number pad. Also, these instructions are on the notes. So you hit the number 9. Also notice that the keys that I'm pressing are showing up in the bottom. So math 9. And so now if you have a newer 84, it's kind of nice because it just lays it out for you and you can just put the things in the right spots. If you have an older one, I'll tell you how to put it in a second. So if we wanted the integral that we were just looking at, so we were looking at 0, you either press the right button or also press the up button to get to the next bound. So we wanted 0 to 20. And then the right button to get over to the integrand field, essentially. And then you want to put in the integrand, which is 3 plus 0.1. Now, technically, in the problem, it was t squared dt. Now, when you're putting in your calculator, the variable doesn't matter. So what you need to press, this is important, what you need to press is you need to press the variable button, which is the one directly under mode. Please do not find X any other way, or don't find T, don't use the little green buttons from the alpha, don't use that. Just use the variable button, which is the one directly under mode. Otherwise, it's not going to work the way you think it should. You needed to square that, scroll over, hit the variable button again. Again, I don't care that the original problem was a T. We can type it in as next on our calculator, hit enter. You should get 326.6 repeating. If you don't get that, I'm highly concerned, but that's what you should get if you punch that into your calculator. Now, if you have an older version of an 84 or you have an 83, life gets gross. So if you have an older version, you're going to start off the very same way. You're going to hit Math 9, but you're going to have to type in your notation like this. So this is how it would look. Oh, my screen's lagging a lot. Hold on one second. There we go. So it'll come up with an FN int on your screen. So in our case, for the one we were just trying to do, what you would have to type in is you want to type in the integrand first. So in this case, it was our 1 plus 0.1. You use that same variable button, and then you'll have to square it using a caret, because again, yours doesn't really do the nice thing where it pops it up for you. You do a comma, which is the button directly above the 7. You hit the variable button again. So I'm going to bold it, comma, and then your bounds, lower bound, upper bound. So if you have an older version, you'd have to type it in like that. If you have, so I'll leave that up for like 5 more seconds before I move on to my TI Nspire. So I know not everyone has like all of them. So I know when I'm going to the different versions, some of you no longer really have to pay attention to that, but come on. I know you're a really old computer, but come on, you can do it. I believe in you. So I have to jump over to my older computer really quick, so it's going to be way slow. But if you have a TI Nspire, what you do, can I have the menu? It doesn't show the key presses. Oh well. So you hit the menu button, you scroll down to calculus, hit enter. And then there's the numeric integral option. Come on, scroll down. There we go. And then just like with the TI-84, it's really nice and it essentially sets it up for you. So then you just have to plug it in the right spots. We have a 0 in the bottom one, 20 in the top one. I think I'm just going to let this go away because it's taking too long. There we go. 0 to 20. Come on. You can do it. I believe in you. And then, so, well, the only difference here is that the TI Nspire can handle different variables. So you can totally put an X, which is honestly what I usually do. I just usually, whoops, that's too many. I usually just do an X. But if you want to on a TI Nspire, if you want to make it match the equation that you had, if you wanted to put a T in there, you totally could. Now that's just for the Nspire. For the TI-84 and 83s, just use the variable button X. But that's how you get it on a TI Nspire. Let me write that down in our notes. I didn't write that down officially. I'll leave that up for a couple more seconds. So you have an Nspire, that's how you do it there. If you have a different type of calculator, I honestly don't know. I'll have to look it up, but you can totally email me if you want me to look it up and I can tell you. But so I know that took a little bit of time, so sorry about that. But for the TI Nspire, hit the menu, go to calculus, go to, oh man, what was it called? Numeric integral? Numeric. And then you just fill out the fields. So that's how you calculate integrals on your calculator. Again, don't get too used to it because we are going to need to calculate them by hand as well. And that's how you do them. If anyone tried to put that in and didn't get 326.6 repeating, then you should probably email me, or if you're the type of person who comes to class on Wednesday, just ask me in class on Wednesday, because usually I can't figure out what went wrong unless I see your calculator. So if you didn't get 326.6 repeating, we want to work that out because you will want to have them actually figuring out the correct values. Hopefully that's what you wanted me to scroll up to, Caitlin. So what we want to do now is we want to try one more in our calculators. If I can scroll back down really quick. I'm going to scroll back down now. I'll wait like 5 more seconds. So we wanted to compute the integral from 0 to 1 t. Now this is actually an example of one we can't do by hand. So even once we figure out how to do these by hand, we couldn't do this one. So we would want to use our calculator. So let me go ahead, I'll demonstrate it in the TI-84 and none of the other ones. But if you have a different type, go ahead and try it. But if you have a TI-84, 83, Math 9, what did we want? We want the integral. Let me do this. Oh, come on. Do the thing. There we go. So I can have it. There we go. So we want the integral from 0 to 1. Remember, you get your E button by doing second division. So do the second division to get the E. If you're on an older version, make sure to put parentheses around the x squared, or else it's not going to like it. So if you have an older version that has to do the fn int, the first thing you'll want to type in is E caret parenthesis x caret 2 parenthesis. So yeah, hopefully no one has an older version because those get tedious. But we have a 84. This is what you'll want to type in. You should get 1.462 blah 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 blah. And if you have something else, you should get the same answer. It shouldn't change from calculator to calculator. But that's how we'll calculate these in our calculator. Questions, concerns on that? Again, if you have a different type, we'll just have to look it up. But all right. So we've got more examples in this section that will not use our calculators for. Haha. So we will want to use our calculators for these in the future. We will learn how to do them by hand, and we'll then do something else with them that we'll be able to use our calculator for. But anyway, so we have the graph here of a function f of t, and we want to know which of the numbers, they have 4 of them, could be the value of the integral from 1 to 3 f of t dt. Explain your reasoning. Now here we don't actually know what the function is, so we can't punch it into a calculator because we don't know what f of t is. So here's where we kind of want to think back to Riemann sums. Think back to Riemann sums. So we want to go from 1 to 3 because those are the bounds of our integral here. So we essentially want this area in here. We really want to find what that actual area is, but since we don't know the function, we can't. So now let's kind of look at some of our options. So let's look at what, a left-hand side and a right-hand side sum would look like if we were just using one rectangle. Let's just make it super simple and see what we get when we even just use one rectangle. Well, if I use the left-hand side, that means I'm using this value right here as my height of my rectangle. Let me actually do it in color. So if we do a left-hand side sum, we're going to get, a rectangle that looks like this. Well, it's got a height of 1 and a width of 2. So a left-hand side sum would be 2 times 1 equals 2. And of course we could split it up into more rectangles, but let's just see where this gets us. And then if we do a right-hand side, and actually splitting it up into more than one rectangle is going to be hard because I don't know what the value is right here. But they do nicely give us the values for the kind of cases we're talking about right now. So if we take a right-hand sum, we have a much smaller rectangle, which has a height of 1/3, but still a width of 2. So our area estimate would be 2/3, which is 0.67, well, 6 repeating, really, if I'm being specific. So what that gets me is that the value must be less than 2, but greater than 2/3, greater than 0.6 repeating. So out of my options that I have, so let me write all the options down here really quick. So out of all the options we have, it can't be 0.023 because this is less than 0.6 repeating. So it can't be that. That's too low. That's lower than our underestimate. And it can't be 11.984 because that's greater than 2. So that's larger than our overestimate. So we're kind of down between these two here, 1.099 and 1.526. Now, in general, saying that both of them might be an option would be good, but let's try to figure out which one might be the better option between the two. So remember, there's another way we can find another estimate. We can find the best estimate that we can find by averaging the two of the left hand and the right hand. So let's go ahead and do that. So let's take the average of those two estimations. This is going to be approximately 1.3 repeating. So now again, both of those are pretty close to that. So maybe that didn't get us much extra, but it was helpful to look at. Now, if we look at that picture that I drew over there with the right-hand side and the left-hand side rectangles drawn on there, if I think about it a little bit, that underestimate looks to be a bit closer to the actual value than the overestimate probably is. Like the area that we're missing in here looks like it's probably going to be less than the area that I'm gaining in here, if that makes any sense. So it looks like the overestimate is probably closer than the upper estimate. So it's probably going to be less than 1.3 repeating. So since the underestimate seems to kind of be winning in that it seems to be the better of the two estimates, that means it's probably going to be less than the best estimate. So the best choice we can pick here is this 1.099. Because the underestimate looks better, I'll say. I know that's not really an official, a very good official way to say it. Now again, if you cut down between the two of them and you said that they were both pretty good estimates, I would agree with you. But if we do a little tiny bit more thinking, it does seem like the smaller of those estimates is probably the safer bet, because the smaller estimate, according to the picture, is probably closer to the actual value than the higher one. So we'll say that this looks like it's probably going to be about 1.099. Now again, we don't know that for sure. We're taking a guess, an educated guess. And again, if you had chose either of those two, I would have agreed with you. If you chose any of the first one or the last one, I wouldn't have agreed with you. Between those middle two, you can make an argument. All of that to just say, we still want to have this idea of kind of doing them by hand and by sight a little bit. So this kind of tells us that if we were to plug this into a calculator, we would probably expect a value around, 1, 1.3, 1.5-ish. So if we were to plug this into a calculator and get 15, we would probably realize that our calculator, we must have typed something in wrong. Anyway, questions, concerns about that one before we go on to the last one? Okay. All right. So this last one, again, we're not given the actual equation, but we want to estimate this integral value. Now remember, the integral is essentially that area underneath that function. So what it's actually asking us for is to estimate the area underneath this function. can do that in a couple of ways. We can do it with a right-hand sum and a left-hand sum, using this graph to the best of our ability, and I'm not drawing. We could find these to the best of our ability and actually use a Riemann sum and all that jazz, and then average the two of them and blah, blah, blah. Which is a perfectly okay way to do it. I shouldn't sound so sassy about it. It's a perfectly acceptable way to do it, but there's another way to do it here, specifically because we're kind of given this grid, layout with the graph. So we're going to do a new way, not really new, but we're going to estimate this area by essentially counting how many boxes we have underneath of this graph. Now, this is just like an extra way, an extra option for how you can calculate these. You can do a Riemann sum. Go right ahead if you want to. But I want to do this kind of extra option of counting boxes is usually what I say. My video stopped working. Oh, that video. Yeah, no one cares. So let's count the boxes underneath of this function. Now, the way I like to do it is I like to start with the full boxes first. So this one's a full box. That one's a full box. This one, that one. And you don't have to actually label them on the graph if you can count them in your brain, but I just want to try to keep track of them. So those are all of my, full, 100% full boxes. I have 7 full boxes. And now I kind of have to figure out how I can combine together the rest of this to form other pieces. So notice these 2 boxes here that are underneath the function. So this piece here and this piece here. Come on, catch up with me. I just need you to do a little tiny scribble. That's all I need you to do. There we go. So those 2 pieces there, notice that both of them are about half a box. I know they're both kind of slightly above half a box, but we are estimating here. So those are both about half of a box. So if I combine them together, that will give me an 1/8 box. Again, we're estimating, so it's okay that it would be a little over an 1/8 box, but those are both about half of a box. And now if I combine these 2 pieces together, that would essentially make another box. So if I combine these 2 together, that'll give me a 9th box. And then what I have left, if I have this area and this tiny little sliver I haven't considered yet over here. That over there sliver is almost so tiny that you almost don't even really need to consider it. But the main thing I need to consider is that kind of right corner that I haven't talked about yet. So if I look at these kind of 2 pieces left on the right, well, they're both more than half a box. So if I combine them together, they're going to be way more than 1 box. So let's say that's about another box and a half. So between these 2, that would get us up to about 10.5 boxes. Okay. Any questions on that? I'm trying to count the number of boxes that I have underneath of this function. And again, I'm estimating it. It doesn't have to be perfect, but I counted the actual full boxes and then I tried to piece together the remaining ones into more boxes. Now, we have 10.5 boxes. Now that doesn't mean that our answer is 10.5. Because we need to take into account the area of each one of those boxes, because we want the actual area. So if each one of those boxes was just a 1x1 box, then our area would be 10.5. But we need to take into consideration the area of each box. Now these are 1x5 boxes. 1x5. So the area of each box is 5. Which means that I can finally estimate the area underneath of this function, which is equivalent to the integral. As essentially, I'm going to write it like this first. The number of boxes times the area of each box. So we had 10.5 times 5, which is 52.5. If you did a Riemann sum, you would hopefully get a value that's close to that. Now, I should also stress, if you decide to do Riemann sums on ones like these, you would have to find both and average them, okay? Which is why I think sometimes counting the boxes can be a bit better. Excuse me. Maybe not better, but it's just, you know, doing one process instead of having to do the same process twice and then average the two. Excuse me, one second. Okay, sorry about that. So essentially with these, because you, oh my goodness, nope, they didn't go away. So on these, you'll see some like this on your Wiley homework. Sorry, I have the hiccups. You'll see some of this on your Wiley homework, and if you want to do the Riemann sum way, you'll have to do both and average them, or else your answer won't come out to be about what Wiley wants it to be. Now, Wiley does have a decent tolerance on this because, again, maybe you say there's only 10 boxes instead of 10.5. That'd be a little iffy, but so there is a bit of a tolerance on ones like these, but it doesn't have a large tolerance enough for like just a left hand or just a right hand because those usually over and underestimated a lot. Whereas in this case where we're just counting boxes and we're trying to get as close as possible to the actual amount of things that are under that function, it estimates it a little better. Now, so to stress one last time, this is a extra option. You don't have to do this count the box way, but if you don't do this way, then you have to do Riemann sums in both directions, both sides, and then average the two. Anyway, so what have we discovered so far in chapter 5? We're trying to find areas underneath of functions. So we've been able to do so with a Riemann sum, and now we can count boxes if they give us boxes. Sometimes they don't give you that graph shape, the grid shape, so you can't use the boxes. But we have our Riemann sums, we have our counting boxes, and if we're given a function, we can actually use our calculator. Because remember, these integrals, that integral notation, is finding you the area underneath of that function. It's finding you exactly what you're trying to find when you're using Riemann sums. So, questions, concerns about 5.2? I'm not seeing any, so, I mean, feel free to type them out if you're still typing. So your quiz on Wednesday is going to focus on 5.1, so Riemann sums. So say you're given a table or a function, can you find a right-hand sum or a left-hand sum, or maybe even both? Now I do want to stress, last time in 5.1, that last example that we did that I couldn't find on the notes, the largest one we did was 10 terms. Usually I stop at about 5 or 6 terms as my max, because if you can do it at 5 or 6 terms, you can do it at 10 terms. It's the same process, just with an obnoxious amount of other terms on it. So I'll never ask you to find a Riemann sum with more than, I'll say 10 to be safe, but usually it's more like 5 or 6 is my limit. But I definitely won't give you anything more than 10 because that's just obnoxious. But that's what your quiz will be on, Riemann sums, on Wednesday. So on Wednesday after, well, before the quiz, after our warm-up, we'll start talking about chapter 6. So we're going to jump around a little bit. We're going to jump over to chapter 6 and then back to chapter 5. But in chapter 6, we'll look at how to do this by hand. How many more quizzes do we have? We have the one on Wednesday. We have the one next week. But then the week after is your third exam. And then the week after that is Thanksgiving. So you only have 2 more quizzes left. The one on Wednesday and the one next week. So 2. So I think we just did quiz 8. So there will be 10 quizzes in total. 2 of them will drop. So yeah, quiz this week, quiz next week. Your next exam, it feels super short, but your next exam is already coming up on the 18th. But anyway, we're out of time. If you have any questions, feel free to stick around. I have a couple minutes before my next meeting. Otherwise,